So I want to start by thanking the organizers for inviting me to this conference. It's nice after all this long Corona break that finally to be able to meet people in real life. I also want to thank Lorianne Jumas for giving me a lift to get here because I missed the last bus from Los Angeles airport. So if it wasn't for her, I wouldn't be here. So the talk is actually it's two things. So what I'm going to tell you about is this stuff I did together with, amongst others, Johannes, who's in the audience, and also with the Selim Joachim group, and that concerns the observation of a few to many body, or the observation of the emergence of a quantum phase transition from few to many body physics. And it's based on these three papers here. And then, if time permits, I will also tell you about some very recent work we have. So this is very much within the scope of this conference, which is this few body physics and how it relates to many body physics. And then, if I have time, I might spend 5 to 10 minutes talking about a new kind of unitarity regime for photons. So let's start with the first topic, and I'll start with a very gentle introduction. So this has to do with the problem of when you make systems larger and larger and larger, when do you emerge? When does this many-body limit emerge? And this is a very soft introduction. This is something that the Greeks already thought about. So it's called the Sorites paradox, and it means they were thinking about if you have one grain of sand, you add another grain of sand, you add another grain of sand, and then at some point they were wondering, you get sand as a material, this plastic material that you can use to build things and so on. So there must be some transition from just individual and few particle behavior to this collective many-body behavior, as we would say in modern language. So this is an old problem, and it occurs many places in nature. So this is taken from a popular slide of my talk to a more general audience, but I don't think it hurts to hear it here also. But for physicists, so these are birds that also exhibit collective behavior that you wouldn't be able to predict just by looking at a single bird. And getting more and more physical and more concrete in physics, if you just take a few water molecules and calculate the properties, it would be very hard to predict this collective behavior, that they can actually exhibit different phases, such as water, ice, and vapor. And this was phrased, one way to phrase it, very nice way, famous sentence by P.W. Anderson, who said, more is different. So when you make systems increasingly large, qualitatively new phenomena emerge. And we would say that we talk about the thermodynamic limit all the time in physics, and we know that in the thermodynamic limit, you can use effective theory. You would not worry about the individual properties of each water molecule to describe this kind of phenomena here. Instead, you would have an effective theory that deals with a few parameters instead of just these millions of coordinates or billions of each particle here. So then the question, of course, is when does this transition occur also in physics? And this has been investigated in many systems. And what I will tell you today is how we use the cold atom, the flexibility of cold atoms to explore this problem within the specific context of superconductivity. And again, it's a popular science. I mean, I've taken a few slides from the popular science talk. So this has to do with what we specifically looked at was this emergence of this broken symmetry phenomenon and this Mexican head potential. So broken symmetry, so here's a magnetic dipole in no magnetic field. It points in any random direction. And if you have a few magnetic dipoles, they will fluctuate and they will be mostly parallel, but still there will not be much order. But if you have a macroscopic number of them, we know that there's a sharp transition at a critical temperature below which they pick a specific direction. They break the symmetry and they just point in that direction because it minimizes the free energy, we would say. So if you plot the free energy as a function of temperature, it has a minimum at 0 magnetic order above the critical temperature, but there's a sharp transition to a minimum at a finite magnetization below a critical temperature. We also know that we have rotational symmetry, so I'm going to talk about two-dimensional systems today. So these needles, these magnetic dipoles, can point. That's rotational symmetry. That's actually what they break, this rotational symmetry, And because of that, the potential is a Mexican hat. So this gives rise to these collective modes. So this is the canonical picture of this phase transition, is that you have this Mexican hat potential, the free energy as a function of the magnetization. And because it has this valley here, this circular symmetry, then you have these long-range Goldstone modes, which corresponds to, this is for an antiferromagnet, it's a bit unfortunate, but it corresponds to spin fluctuations when the order parameter moves around here, whereas the fluctuations in the size of the order, we call, at least in high energy, we call Higgs mode. We are going to investigate this phenomenon. So it's the same language that appears in many energy scales in physics, this thermodynamic description of this phase transition. What we are going to investigate with Selim, or what I'm going to tell you about what we did, is this picture in the superconducting, within that phenomenon. So we have a bunch of fermions spin up and spin down, red and blue. They interact attractively. And if there are many of them, we know that they will Cooper pair below a critical temperature. We heard several talks referring to that already. And the Cooper pairs, loosely speaking, have a wave function, which is the gap. And the gap has a size, but it also has a phase. And because these Cooper pairs, they they overlap in space, they decide to lock their phase. Just like the magnetic compass needles here decide to pick a given direction, they also pick a specific phase. So they again break a symmetry to form a superconducting state. So it's the same phenomenon as up here. And the question we will now try to answer is, how many fermions do you have to have for this phenomenon to occur? This thermodynamic, intrinsically thermodynamic picture, how many fermions do you need? And it's not only an academic problem, and I know there are many nuclear physicists in the audience here, so I should be careful what I say. But in the nucleus, this is a mesoscopic system, and you have nucleons, neutrons, and protons, and they also pair up. So you also can talk about pairing in the atomic nucleus. And the reason that these are actually very old papers. I started to look at this problem a long time ago, was because there was a postdoc at the Niels Bohr Institute when Ben Mottleson, who won the Nobel Prize for worrying about collective phenomenon and pairing in the atomic nucleus, was also, so we started talking. And in those days, these new experiments were emerging of atomic gases. And we said, why don't we just look at this emergence of pairing in mesoscopic atomic gases? Because there are fewer, as you know, much better than me, unknown parameters in these systems as compared to these atomic nuclei. So we worked on that. Unfortunately, it took a while for the experiments to get there, but now they are here, and it's basically been spearheaded by the Jochen group in Heidelberg. So here's an early paper where they saw the emergence of a Fermi C. They had one impurity particle, and they added more and more fermions, and they saw that at some point the energy of this thing, this impurity atom, started to behave like what's called a Fermi polaron. And recently, I discussed with him at many conferences, and finally he built this two-dimensional mixture I will tell you about later of two different fermions. And so we now have this problem here in a harmonic trap. It's in 2 dimensions, and now he can start studying pairing correlations. And let's go to the thermodynamics. Let's assume that this system is indeed thermodynamic. It's at 0 temperature. So they are paired, they have broken the symmetry, and let's see what happens. So we have our 2 different fermions in our trap, and you have 2 kinds of pairing. You can form Cooper pairs in 2 different ways. Either the fermions can form Cooper pairs between shells, or they can form Cooper pairs within shells. And in most cases that you're used to from the experiments that were being referred to by Martin Spierlein, for instance, you have many atoms, and the pairing gap is much larger than the level spacing. So then intra-shell pairing dominates totally over intra-shell. You have many more possibilities to form Cooper pairs between shells. And another way to say this is that the size of the Cooper pairs is much smaller than the size of the trap, the cloud, not the trap. So you have local Cooper pairs, and so you can basically do local density approximation to describe the system. The regime we are now interested in is this regime here. This is also what's more relevant for nuclear physics. That is that the pairing energy is smaller than the level spacing. And this is the regime that you have in nuclear physics. And when this happens, then the intra-shell pairing dominates. They don't have enough pairing energy to start making pairs across the shell. So it's a different regime. And you can do a lot of tricks, and I'm just going to flash, I'm not going to say, but what I did in that paper was you can just solve that problem. And it's a little bit more complicated than solving pairing in a homogeneous system between k and minus k. You now have harmonic oscillator levels and so on. But you can do very controlled approximations. A lot of them I stole from nuclear physics. And you can actually solve this basically as an analytical solution of the problem of intra-shell pairing in a harmonic trap. You get some sums, you have to sum and Riemann zeta functions and so on, but you can solve it. And let me just tell you what the results are. And you can recover some exact results. But I don't have, I realize I only have 30 minutes, so let's not go inside. Let me just flash you the main results. So there are two different, and again, for nuclear physicists, you will know this very well. But for atomic physics, maybe not so much. So there are two specific cases we need to focus on. One case is if you have an open shell. That means that the highest occupied shell is partially occupied. Then for any attractive interaction, you always get pairing. And you can calculate analytically the pairing function. This is not the case that I will be focusing on. I'll be focusing on this case instead. And that's a closed shell case. So that's the case where the highest occupied shell is completely filled. It's what nuclear people call magic number configuration. And there you need a finite you need a finite attraction for the system to become superfluid. And that's basically intuitively because to make Cooper pairs, you need to make coherent excitations across the gap. And that requires a finite energy. And you can again do, so you have this quantum phase transition, you would say. You can do analytical stuff for that as well. But you have a quantum phase transition in the magic shell configuration so that the system is normal for a given interaction strength. You crank up the interaction strength, and then it becomes beneficial for the system to become superfluid. And here you can see that then you should get associated with that transition, if the system is thermodynamic, if my description is correct, you should see a collective mode that becomes flat at the phase transition point. And that's this pair fluctuations. The collective mode should correspond to spontaneous excitation or to excitations of time reverse pairs across the gap. That's the prediction from a thermodynamic theory. It will cost finite energy if the attraction is not strong enough. It will cost zero energy at the transition point, and then it will cost the energy 2 times delta actually, which we will see. Yeah. And when you compare, I just want to flash it, when you compare this with numerical solutions of what's called the Bogoliubov-Deschênes equations, it's very accurate. So all these analytical results assume pairing between time reverse states in the harmonic oscillator states. And if the pairing energy is small compared to the level spacing, it really is a good assumption that you only have pairing within shell, the same shell of time reverse states. So we have this, it predicts the space transition, and let's look at the excitations above the ground state, because this is what Selim is going to look at. So we do what's called, so we basically just calculate the fluctuations of the order parameter living in this Mexican head potential here, using standard techniques. And again, because you only have pairing between time reverse states, you can do it. And this is what you find. So you find, let me show you what you find. So for a normal phase, if the interaction is not strong enough for the system to become superfluid, you find a mode that actually goes down in energy. It starts at 2 times h bar omega, but then when you increase the attraction, you find that the energy goes down. It follows a specific expression you can calculate. And that's because when you have attraction, when you excite time reverse pairs across, they can utilize the free density of states up here to maximize their overlap. And this decreases the energy below the non-interaction energy, which is 2 times h bar omega. And then you can calculate that. And this is how let me focus on the closed shell case. So so you can basically calculate this Higgs mode, this amplitude mode, connected to the fluctuations in the order parameter, and it goes like this, and then it goes 0 at the phase transition point, and then it goes up again. This is now a thermodynamic calculation, but we are interested in when is that picture correct. And then this is where now also the topic of this conference comes into play, and we have one of the guys, Johannes, is here in the audience who did this calculation. So now we approach it from the opposite regime. We just say, okay, we have a few particles, and we just solve the problem, and on a computer. And I just say, that's a very hard problem. So we just solve the problem, and we see what comes out. What does the computer spit out? There are some technical problems because we work with the delta function interaction. You have to regularize that. We heard several times this morning. Here's what comes out of such a calculation. What Johannes did was he put 3 fermions to spin up and 3 fermions to spin down into a 2-dimensional harmonic trap. And then he looks at the excitation spectrum above the ground state energy of monopole kinds. There are monopole dipoles and quadrupoles and so on. And what he sees is he sees a bunch of states up here. This is as a function of interaction strength here. This is the excitation energy spectrum. They all start at 2 times h bar omega for 0 interactions because we're looking at monopole transitions. Then you see a bunch of states that go upwards in energy. Those are not so interesting. They just reflect the fact that when you have an attractive interaction, there's kind of a Hartree potential that makes the trap tighter with increasing attraction. And so these energies go up. But there's one mode that's qualitatively different. It goes down and then up again. And this is the thermodynamic prediction, is that indeed there would be one mode that would go to 0 at the phase transition point and then up again. What he sees in the few body calculation is a gradual, it just goes down and up again. And when he goes in and looks at what does this mode consist of, he has a wave function, he has access to everything. It predominantly consists of, where he sees the wave function for these excitations mostly consists of those incoherent excitations of a single particle 2 shells up. This mode here consists of coherent excitations of time reverse pairs 1 shell up, precisely from what you would expect if you had a Cooper instability. The system kind of feels that it wants to be superconducting, but it's not large enough to do it. But it really likes, there's one mode that costs less energy. That's the one that excites time reverse states 1 shell up. Then they can utilize the attraction up here to minimize the energy. Then you can see, so the phase transition has turned into a crossover region. Then he went to 6/6, and this mode deepens. So you can see how you now start approaching the thermodynamic limit. But I think it's fair to say, and Johannes can maybe elaborate on that, already at 6/6, it's not converged. So this is the limit we are at. So we have a thermodynamic limit, and we have 3+3 under good control, but already at 6/6, we're in trouble. So here, I mean, if there are experts in the audience, it would be very nice if you could go further down here. And now let's just let me, as a theorist, present the experiment. So what they did in the experiment was they had a 2-dimensional pancake trap of lithium-6 atoms in 2 hyperfine states, and they had interactions between them were tunable with a Feshbach resonance. And they had this spilling technique, so they can actually make magic shell configurations. So they can actually in a deterministic way produce systems with 2 particles, 6, 12, these magic shell configurations with high fidelity. So this is really a great setup. And what they then did was, which I skipped, I'll tell you, they excite the system, not by shaking the trap, because it turns out that the Higgs mode, that's another prediction we have, is not strongly coupled to density oscillations. What it is coupled to is modulations of the interaction strength, because if you modulate the interaction strength, you modulate like the attraction. You start making like this to the Cooper pairs, and that's precisely the you couple strongly to the size, to the magnitude mode, amplitude mode it's called. So that's what they did, and they did that by shaking the confinement, and in that way, in the z direction, in that way you actually modulate the interaction strength because the wave functions become more overlapping. And here's what they see as a function of this excitation frequency. They count, so they start with a magic shell configuration, and then they see we start 6 particles, nothing happens, and then when they modulate it with a given frequency, they count how many atoms they have left after this experiment. They either have 6 or 4. So they lose particles in pairs, precisely from what you would predict if it was this kind of Higgs precursor, this amplitude precursor mode, because it's excitation of time reverse pairs. Then they also see these other modes that are at a frequency higher than 2 times h bar omega, and there you lose particles either 1 or 2 or 3, and that's because it's just kind of boring single particle excitations 2 shells up. So here you really see what you would expect from this picture, this few body precursor of a thermodynamic picture. And here they do it as a function of interaction strength. They plot the modes for 2 different particle numbers, and when you start analyzing it theoretically, I mean, this is not a perfectly harmonic trap. I can show you slides with that if you want to see the precise comparison of the theory. But nevertheless, for this talk, I will just tell you that you can identify this mode here. This is this few body precursor of the Higgs mode. There's another mode you can see that's also non-monotonic, going down then up again. That is associated with non-zero angular momentum pairing, because it's not completely spherically symmetric, rotationally symmetric, this trap. When you modulate the trapping frequency, you couple also to L plus minus 2 modes. So this is finite momentum, angular momentum pairing you see here. And so I can show you details on this if you're interested, but you can also theoretically model these experiments, as I said. And what you see from the experiment is that this mode has the characteristics you would expect. So it has a non-monotonic behavior, which is a precursor of this Higgs mode. It's predominantly consists of excitations of time reverse pairs, and it's strongly coupled to modulating the interaction strength and weakly coupled to modulating the trapping frequency, also as what you would expect. So in that sense, you have seen now the few body precursor of the Higgs mode, and you have seen this onset of you've seen the onset of this thermodynamic picture, but they are not there yet. So you can see that the mode is not going to 0. If I go back, you see the mode frequency is how far they've gone down is down to 1. They go from 2 down to 1.4, and you really would like to see the modes going all the way down. So that's an open problem. So this is kind of this work. And we think it's fun to say that it's the same kind of physics. I know that it doesn't have this couplings to generate mass, but it's still funny that it's the same kind of physics we see in these experiments as you would see in huge accelerators, for instance, at CERN. Okay, so let's skip the theoretical modeling. So we can do some theoretical modeling on this. So these are the people that did this work. So Johannes is in the audience, and Steffi is a theoretical physicist at Lund University. So they did the few body calculations. And here's Joachim's group at that time. And just to, since this is a KITP conference and it's sort of open for discussions and so on, I think there's definitely room for experts in the audience if you can go beyond 6 particle systems and see if you can do something systematic to see how this onset of this thermodynamic limit comes about, because we have a huge gap between the many body picture and the few body picture. And one thing that I talked about broken symmetry, but then I only talked about the amplitude mode. I never talked about the phase mode, this spin fluctuation mode, or the goldstone mode. And that's because they don't see it. Because for the experiments, they're working on that now. but it would also be nice to see when do these modes appear theoretically. We know when they should appear in the sense that they should appear when the size of the Cooper pairs start to become comparable to or smaller than the size of the cloud, because then you can start defining a local phase of the Cooper pairs, and then you can start talking about phase fluctuation modes. The experiments so far, I think, Johannes, maybe you remember, but they're at the limit where the size of the Cooper pairs becomes smaller than the size of the cloud. But I don't have a theory for how to go from here to here. So that would also be nice to do. I've talked to several people on various, I think it will has to be numerical in some way. And so that is related to how this Goldstone mode spectrum changes from how the collective mode spectrum, or the mode spectrum changes from being single particle excitations to collective modes, and also to something. It would be nice to see the reduction in the moment of inertia and so on. So that finishes the first part of the talk. And then the second part of the talk, I will just very quickly run you through a recent paper we have, which has to do with strong interactions between between photons. So this has to do with the unitarity theme in this conference. So how can you make strongly interacting photons? And the basic object of this second part, which will be a little bit fast, is that you can create particles called polaritons, which are a coherent mixture of a matter excitation and a photon. And then the idea is, and they can be created both in the solid state, where the matter excitation is an exciton, and they can also be created in atoms, atomic gases, where the matter excitation is an atomic excitation. And this is the mechanism for generating slow light, because when the photon is coupled strongly together with an atomic excitation, it acquires a mass and it becomes slow when it propagates through the medium. And one thing that's nice, one thing that drives this, making these polaritons, there are many nice properties about them, but you have the opportunity to make light strongly interacting at reasonable energies. So we know that it's not strongly interacting because the scattering process in a vacuum is off resonant between two photons. But if now you can make them interact via the matter component, then you have an opportunity to make interacting light, and this has created this whole field of quantum fluids of light. And you have indeed seen effects of interactions, so you've seen many things. But basically, the interactions are too weak to generate strong interactions. And basically, since I have 3 minutes left, I can tell you that we have very recently provided a way to generate strong interactions. The idea is basically to use what you know and love, phase back resonances between the atomic parts, and then you can make the polaritons strongly interacting. There is one surprise in this work, and I will skip the theory and just tell you what the mechanism is. And that is that you find that the interaction scales, that the interaction between these polaritons coming in, so this is now a mixture between an atomic excitation and its atom and a photon, atom and a photon. They come in and they scatter and they come out. And what you find is that the interaction can be very strong between these two polaritons, even though the bare interaction between the atomic parts is weak. So this is what surprised us. But when you think about it, the mechanism is fairly easy to understand. The thing is the following. When the two polaritons come in, so this is now a superposition between a photon and an atomic excitation. The two atoms have a bound state, so they have a positive scattering length with a bound state, and it's sitting down here compared to the two polaritons coming in. This is an energy, sort of an energy. Then because these two atoms forming the dimer here are also coupled to light, there are some things that you should ignore here. I can explain to you in the break. That also shifts the energy of the dimer. And what you can do is you can play with this 3-level scheme I showed you to shift the energy of the dimer while keeping the incoming polaritons constant in energy. You want to keep them constant in energy because if you want to have EIT, this lossless propagation, that's a very strict condition for them to be lossless. So that you want to keep those constant energy, and then you tune the molecule up and down with some light field here, and then you can actually tune it into resonance. And that's the mechanism between generating strongly interacting photon. And what you find when you do this, you can do it's basically an exact solution of a two-body problem of two scattering polaritons. So there are no approximations apart from the fact that we assume a short-range interaction. What you find is that you can find a resonance scattering between the two polaritons that scales with 1 over a squared. So if the matter part of the two photons, of the two polaritons, is weakly interacting, you can tune it into resonance so that the interaction between the two polaritons becomes very strongly interacting. So the weaker interacting they are, the stronger interaction you can make the polaritons. And this is, we think, is a funny result. For theorists, it has to do with the fact that the bound state wave function of these two polaritons, or these two matter components, is a Yukawa wave function. And if you see how that couples back to the scattering problem, it actually couples back with a 1 over a squared. So that's where the origin is. So you can generate strong interactions between polaritons, much stronger than the interactions between their underlying matter component. And now I think time is up. So thank you very much.
Thank you for this really interesting talk. It's open for questions.
Do you have perhaps an example, a concrete example for realization of this polariton idea? What kind of molecular states would you be thinking about? Yeah, that would be interesting.
Yeah, I mean, we plugged in some numbers for rubidium. We can talk about it. There are many parameters in this scheme, but if you plug in realistic numbers for rubidium with a scattering length and a bound state and realistic couplings that you can generate with light, you can get magnifications of really big factor compared to the bare cross section between the rubidium atoms.
So these are ground state rubidium molecules.
Yeah. So if you can make polaritons in this system, I mean, I don't think it's a difficult experiment. Yeah.
No. Oh, thank you very much for the very great presentation. I have a question about when you discuss the gap between the intrashell or intershell.
Yes.
If I understand correctly, you did that in 2D.
Mm-hmm.
Do you expect a similar effect also in 3D?
Absolutely. I mean, it's actually better in 3D. It's even more pronounced in 3D.
So why did you do the calculation in 2D? Because
helium cannot make 3D. So first we did it when we inspired by the nuclear stuff. Nuclei are not pancakes. I mean, they are three-dimensional objects, and you have the same effect completely. I also wrote, and this is what I did with in these papers with Ben Mottleson. We looked at this stuff in 3D, and it's the same. But then because helium makes pancake traps and not round spherical traps, and we did it in 2D also. Yeah, it's better in 3D. It's a bigger effect.
Thank you.
One question I had for you is trying to relate what you showed at the end of the interacting polaritons to the Vulitic type work, where I think they've realized interaction between the photons, but I believe that's all one-dimensional in their context. I mean, is there some connection between what you've discussed and the Vulitic experiments?
Yes, I have maybe. I'm not entirely sure, but I think theirs was anti-bunching, wasn't it? It was. Did it have to do with Rydberg?
Yeah, they claim to see actually photon bound states, 2 photon bound states, and then there was follow-up theoretical work predicting Efimov states of the 3 photons, in a polariton sort of environment?
Yeah, I must confess, I mean, I remember that paper, but I don't, it's a different mechanism they use, but yeah, that's a good question. I have to look up. Yeah.
We both wanted to give it to you.
Well, thank you. Is it working? Oh, yes.
Yeah.
I have a question on the polariton experiment data that you showed, or the idea that you showed. So which mechanism did you consider in order to change the energy of the molecular state? So I assume that the molecular state for polaritons in a semiconductor is biexcitons. So how would you change this energy? And then maybe a second part of the question. So you said that there is an enhancement as compared to the bare scattering cross-section. Does this really now allow you to bring the full gas into a strong correlation regime? Or is it sort of an enhancement on top of a very small interaction?
I think for the latter part, I think it is. I don't see. I mean, you get basically resonant scattering between the polaritons, but this is now scaling as so the cross section scales as 1/a squared, and I think this is. But then, how to build that into a many-body environment? Then you have this problem that you have you cannot just do this to do mean field theory for this. So here we just calculated the cross section, the scattering matrix. To then do many body theory on top of that is then, as we know also from cold atoms, a challenge. But it is strongly interacting. Regarding the solid states, it's a little bit subtle. It's because I ran out of time. But what you need to make what you use when you shift the molecule and not the incoming scattering particles. So you can move this molecule up and down while keeping those two here constant. Is that you have this 3-level scheme, and so you have 2 light fields, and you can play when you play with the strength of this off-resonant light field. Then you can move this up and down compared to while keeping those constant. I can show you in the coffee break. And we are now working on how to do that in a solid state setting. So in a solid state setting, here's what you need. You need this 3-level scheme, as the atomic physicists know very well. So you need a photon that couples to some excited state. That excited state is typically lossy, but then you have a classical field that couples down to this state here, which is the one that forms this bound state. And it's this one you need to be able to tune to the strength of this field here to keep the polaritons, which is the superposition of a photon and this excitation, constant in energy while this dimer starts moving up and down. How would you do that in a solid state setting? That's what we're working on right now. So here, the photon is a photon. The short-lived state, where you excite up, is an intra-layer exciton. They can make these 2-dimensional layers. And then you have, and they have already demonstrated that in several experiments, the electron can tunnel to another layer, and then they can form these dipolar excitons, and they are extremely long-lived because they the wave function of the hole and the electron do not overlap. So this tunneling here, so this creating an exciton corresponds to this process here, photon, and then the tunneling to another layer corresponds to this excited state here becomes an interlayer exciton, and that's long-lived. And this tunneling is tunable by rotating the 2 layers. So we think you can also do it in a solid state setting, but that's what we're working on because the devil, of course, is in the details, but the ingredients seem to be there. Then you have to worry about how can you create bound states between these 2 interlayer excitons because they repel each other. But if it's in a lattice, you have repulsively bound state, as you know. So you did that with the, yeah.
Was there another question in the back of the room?
Please, I have a
Oh, you have one. Okay.
When you show the calculations to analyze the transition numerically, you show the calculation for 3 times 3 and then 6 times 6, and then you stop it, say you have problems to continue. Can you give an idea of the method you are using and which are the problems you are facing to increase the number of particles?
So that's a question for Johannes, who's sitting right next to you, so you can give him the.
Yeah, so what we try to do with this was to keep it at as a very simple calculation in terms of we wanted to use harmonic basis states, and we just wanted to use as many of them as possible. Because it turns out that the effect around the transition really grows from the collectivity. So we tried a number of different ways to choose specific parts of the Hilbert space, but none of them really worked. It really was an effect that was collective in the sense that you really had to crank up the number of basis states. So the problem was basically both in terms of storing the matrix in the computer and actually performing the diagonalization. Although we have some work on where we apply the generator coordinate method to actually go to higher particle numbers. It's still an approximation, but we can get pretty good upper bounds for these excitation energies. So we can see actually the same thing continuing for 12 plus 12 and 20 plus 20. But of course, it's a problem that you have to have the filled shells as well. So it's not like the next step is 7 plus 7, but it's actually 12 plus 12, which is of course hard. But with Hartree-Fock-Bogolyubov on generator coordinate method, we have actually been able to see something where you see this minimum going down even further. But to answer like with one sentence, it's just a matter of time constraint and computational resource. I hope it answers somewhat.
I mean, you can do all this Hartree-Fock-Bogolyubov as Johannes said, but then it doesn't fit with the. It doesn't go from the. It doesn't recover the exact results for in the few body limit. That's the problem.
You always have like the few body gap.
Yeah. Yeah. Anyway. Yeah.
Yeah, you always get a few body gap. As long as you're not in the infinite limits. But of course, if you can see, so what would be interesting would be to continue towards 12 and 20 plus 20 and 30 plus 30 and maybe fit the scaling function. So then one could do finite size scaling analysis, and then one has one more piece of the puzzle to show that this actually really, you can track it all the way down to infinity. But for now, it's not sufficient to have 2 data points to do a few finite size scaling function. But maybe if we get 2 more data points, we can actually fit the scaling function. So that could be something.
I have maybe a follow-up question, which is, so these mesoscopic systems, you're talking about Cooper pairs, but actually it's few to many. So in what sense are they Cooper pairs? I mean, can you see the emergence of like a long range, off diagonal long range order when you build up the number of fermions in a trap in a few body model? I mean, in the B2G, you assume this, right?
Yeah, so we didn't look at the off diagonal long range order in the density matrix, but what we did look at again was we looked at the wave function itself. So you can look at how does the number of does it consist mainly of superposition of time reverse pairs? And this is correct, right, Johannes? That you see that you see again that the fraction of the wave function that consists of the superposition of time reverse pairs goes up at the transition point smoothly. Experimentally, they recently tried to do expansion, or they did expansion experiments. So you would expect to get when you switch off the trap, then you would expect to see K and minus K correlations, and they also see things that look like you get like an increase in that. One problem is that it's a few body system. Another problem is that it's actually not K and minus K that pairs up. It's N and M and N and minus M. So it's not K and minus K. It's angular momentum states that are paired up, and that blurs the signal. But this is also something we are looking at.
Okay, I think everyone's satisfied. Let's go.
I have one more question.
We're not have everyone satisfied.
No, very small question. In the last, no, because I was thinking in the last part of the talk, no, when you show the dimer and the excitation, you have access to the dimer energy.
In this plot here.
Yes.
Yeah.
You have access to the dimer energy.
Yes, this you have access to. What do you mean access? In what sense?
You know the dimer energy.
Yes, from the scattering length. Yeah, it's just 1/ma squared. Yeah.
Okay, so lunch is being served out in the courtyard. Let's thank him again.